I am a final year master student in electrical engineering in IIT Bombay. So mine is going to be a very short presentation on the latency work that we have started doing in the stochastic systems lab at IIT Bombay. So the broad topic is towards enabling ultra low latency applications over Wi-Fi. The outline of the presentation would be, I will start from the background and motivation, then going up to experimental settings, results, conclusion. So this augmented reality, telehaptic communication, and autonomous vehicles, cloud gaming are just a few emerging applications that require ultra low latency and high throughput to work seamlessly. So such stringent requirements need protocol support from MAC by prioritizing different traffic types. We plan to develop scheduling algorithms within the framework of latest Wi-Fi standards. So in this work, we initiate a study of different levers that can be pulled to enable low latency communications over Wi-Fi. In particular, we want to see the effect of packet marking over on latency by allowing preferential treatment to different traffic flows. This talk would give you a sense of learning curve that I had as a student and how we want to use Wi-Fi for our purpose. My focus would be more on the practical side, and I'm sure most of the audience here has a lot of experience in this domain, and for someone like me who is just getting started, it would be very interesting to know your views firsthand. So getting started with, so the application that got us motivated to do this work is this telehaptic systems. So what happens here is there is one operator and one teleoperator. The teleoperator tries to mimic what operator does, and in turn it gives a feedback signal in the form of audio video. So there are many challenges in the telehaptic communication if you want to do it over Wi-Fi or wirelessly. So it includes extremely sensitive and critical operations. Any standard update rate of haptic signal should be maintained at least at 1 kHz. The conditions on the network parameters for a smooth telehaptic communication are very media specific. So this chart will give you an idea of that. So for audio, we know one-way delay can be maintained at 150 milliseconds roughly. But for haptics, we need to maintain that at 30 milliseconds, which is 5 times lesser than any audio or video signal. But there is some space in the packet loss. We can have some packet loss because this is a real scenario. So if we don't get if we lose some frames, then there is no point of getting that frame at future time. So we can have some packet loss, but there should be in a limit which is maintained at around 10%. So yeah, so this is the challenges in telehaptic communication. So this is a schematic diagram representing the telehaptic communication for operator and teleoperator. So this is just what I have mentioned, this forward channel and backward channel. And to do this in a dedicated network or in a LAN setup, it would be very easy because we don't have this non-deterministic network behavior, and those are not vulnerable to QoS violations. Yeah. So just to recap what we are doing. So we are trying to use packet marking to see the latency. So that falls under quality of service. And by default, internet is best effort. So queuing and bandwidth management are required for priority access. So and the traffic management is done using classification and marking tools. And this should be communicated at each node of the hop to get the implementation of QoS. So what is the aim of QoS? The aim of QoS is to reduce probability of collisions for high priority traffic. And for getting the medium access, Wi-Fi uses CSMA-CA, which is implemented using EDCA. And what EDCA does, it involves like different contents and window sizes and DIFS timers for different type of access categories of the traffic. And in downlink, it maintains a priority type of queue for different access categories. So if you see in this diagram, this is a four access priority traffic. One is background, best effort, video, and voice. But simply having a queue does not give you quality of service. It depends on how you manage the queue and what the scheduling algorithms that we are using for different type of queue in the downlink. So now I will like jump to what we are doing and how we are like implementing the packet marking. So packet marking can be done at the source also of the senders. That can be done using this IP tables in the OS kernel, Linux OS kernel, or it can be done at the AP access point with the help of these firewall rules. Now, in summary, what are the network requirements that we have? So, what that we want for the telehaptic communication to succeed? First is the ultra low latency. Of course, high throughput we need. We can have some packet loss within a limit. We are using shared wireless network, and of course, we chose UDP over TCP because TCP involves a whole lot of management frames and other congestion and bandwidth management that we don't want to do here. And at last, quality of service, and we want to also use this uplink OFDMA we want to test this uplink OFDMA as well. So that side gives you a complete cycle of the Telehaptic. What are the things that can be optimized there? First is the video capturing, all this encoding, decoding, that are different parts that could be optimized for a low latency, but our focus was on the networking part. So these are the networking requirements that we want to have. Now this just shows a block diagram of what are the code that we wrote, like what are we using here. So it's basic client server model, multi-thread servers, UDP protocol, clock synchronization, and all the analysis are done using Wireshark. Now coming to the challenges that we faced while doing this experiment, because we are not using any simulator or any kind of thing. We have written the code from scratch, and like everything we are doing from scratch. So generating high data packet rates is a bit of challenge because the sleep time that, for example, suppose we want to generate 10 Mbps data, so we will have the packet interval within some milliseconds, and that is hard to get in a operating system that much resolution. And as we increase the like data rate, it will become lesser and lesser. So getting that high data rates would be a challenge. So earlier we started with a large bandwidth channel, but then we switched to a lower bandwidth channel so that we could block the network with fewer devices in the network. Second was this packet drops and impact of RF environment, because we are using this shared network. So there were times when we could see a huge packet drops, unusual traffic behavior. So a lot of time went to analyze where the packet were dropping, which buffer it is dropping, and what is the effect of RSSI on the throughput and latencies and all these things. So monitoring RSSI values, packet drop, buffer size, and all these things. And third was this calculating one-way latency using time synchronization. So because we want latency, because if we want latency within few milliseconds, so if we have this clock offset, so challenges, there are many challenges in clock synchronization using NTP. So if we use this, NTP within a LAN network or wired network, we can get offset of around 3 to 4 milliseconds. But when we move to wireless, it increases to around 10 milliseconds. And if we have latency and the offset in the same order, then it will be very hard to determine what is the exact latency. So what we have used is we have used some kind of hack to do this. So we are using we are calculating offsets at each periodic interval, and after some time we are also using this wired LAN connection to synchronize with the NTP servers. And then when so we are updating the process when we see that the real clocks starts to drift within a few error margin. Yeah. So coming to experiments and results. So this is the first setup that we had. So here in the sender side there are two senders, and there is one receiver which is receiving one common receiver. So these two senders are trying to send data to the receiver, and all these three are connected to a common Wi-Fi channel on the 5 GHz band. So we are trying to push high throughput data through this, and we are seeing what is the effect of marking in this network. So we did 3 of them, so 3 experiments. First, best effort traffic on both the sender 1 and sender 2. In the second, there will be the traffic of sender 1 will be marked, and in third, the traffic of sender 2 will be marked. So here in the left hand side of the figure, if we see, when there is no marking in the x-axis, if we see when there is no marking, the application layer, the rate at which the data is pushed from the application layer is maintained at around 23 Mbps for the sender 1 and around 14 Mbps for the sender 2. Why there is a difference for sender 1 and sender 2? Like we found out, like the device, it's basically due to the device configuration, and one of the devices was very old. So if we use the and we checked it, if we are using the similar kind of CPU on both the machines, then we are getting an equal rate for the no marking case. So going to the second one, when we mark the sender 1, okay, this slide is, I think, okay. So if we see the sender 1 rate, when we mark it, the data rate improves from 23 to around 30 Mbps for the sender 1, and sender 2 it reduces from around 14 to around 8. But the aggregate rate is same for all the three. And if we see for sender 2, it goes from 14 to around 20 when the sender 2 packets are marked. Now why is this happening? Because if we see in the right hand side figure, that is the figure for when sender 1 is marked, and this is the figure for transmitting time of sender 2, right? So if we see the first half of the packets, the time for first half of the packets, what is happening, that it is the time it is taking a lot of time for the first half of the packets. That is the time when sender 1 was getting most of the channel access, and sender 1 completed its like sending all its data when the sender 2 completed half of its data, and after that it is getting the entire channel, and it can use the entire channel. So in this figure, so in this first setup, we didn't capture how this AP is scheduling, like differentiating between the marked and unmarked packets. So for this, we have this second configuration where we are pushing the data through a wired network. So all the data are being received at this AP, and now we can observe how this AP is differentiating between the marked packets and the unmarked packets in the downlink. So this plot, if you see, so this plot shows this in the x-axis we have different rates at which we do the experiment, and in the y-axis it is the latency. So as we move from, as we see in the 7.5 megabytes per second per sender, so in total 15 Mbps. In the second 7.5, 8 and 9, if we see on the right hand side, so the difference between the green and the red one, so that is so green one is the sender 1 and red is the sender 2, and green one's packet is marked. So if we see, the marked packets has quite a bit of like very low latency compared to the unmarked packets. So for the 7.5 megabytes 7.5 case, we can see the latency for the S1 is around 10 milliseconds, but for the sender 2, which is unmarked, it is around more than like 5 times more, 60-70 milliseconds for that, and that is consistent above all these rates. So so this was the bottleneck basically of the link that we are using, 20 megahertz link we were using, and after that there were packet losses. After, if we move from 9 to 10 Mbps, there were huge packet losses. So this was the major conclusion that we saw in the downlink when we mark the packets versus when we don't mark the packets. So yeah, this was the effect of packet marking that we saw. Now moving on to this. Now this Wi-Fi AX promises us a lot more in the terms of newer concepts like OFDMA and TWT, but it's still early for me to put up any slide for that, because we are still testing. So just what is OFDMA? I put up this slide. And secondly, we want to test this feature as well, TWT, because it promises optimizing spectral efficiency by reducing contention and overlap between users. So if we don't, if in a high throughput, high density network, if all the clients don't contend at once, so we will get a very, the traffic, so we'll get the airtime will be much more scheduled with the help of TWT. So we wanted to test this as well. Now coming to conclusion, so we saw this packet marking can help reduce latency, differential and reduction in overall latency can be seen, but there were huge packet drops as well, and we are exploring these features. Coming to future scope, with the setup and all these things in place, we plan to carry out many more experiments with multiple APs as well. So now we were just focused right now on the latency part, but at some point of time we want to improve the reliability as well. So some compromise on the latency has to be done to improve the reliability of the packets that we are planning to do. And we are planning also to test some scheduling algorithms within the AP. And final goal of our is to do this end-to-end telehaptics operation over to get a complete wireless experience. Thank you.